Hi guys. Well, it has been a while. That was a roller coaster the last 2 weeks. That's my first video since I had the problem with the food poisoning that sent me to the hospital almost 10 days with a kidney failure. Yeah, guys, a kidney failure from one sandwich. It was awful. Yeah. Thank God I made it out quite fast with almost no casualties. I'm still in recovery, but I'm so much better again. Yeah, so be careful what you're eating in this hot weather. One sandwich sent me to the hospital, yeah, and it was a fresh sandwich, yeah, and it was not done, no nothing, yeah, it was just a little ham and cheese. The problem was I had an egg inside, and that killed me. Anyway, I hope you're still all here. This is my first video, as I said, after my recovering. And again, of course, it's a video of a power supply. And why? I see that these power supplies here are getting so much interest from from people that these cheap power supplies they're used everywhere. And some while ago, when I made the video about the 300 volt 1.6 amp regulated power supply, I got the complete reverse engineering, and I showed the schematic. I got many questions on how the current regulation works. Well, the easiest way is just not blah blah to say it, it's to show it. So let me show you. So here we have the schematic I made, the complete reverse engineering of the power supply. Has been done donkey years ago. Yeah. And since I made the video showing this schematic and explaining the schematic, I got quite a few questions on how the current regulation works. And I can imagine that this is interesting for quite a few people because this is not that trivial here. On the one side, it doesn't look trivial, but it is trivial. So let me show you. Let me zoom a little bit more in. And we have here the shunt. There are two shunts in parallel, two constant Dan resistors in parallel, very, very low ohmic. Together, I think they have 1.5 milliohms. This is way, way, way too low for 1.6 amps. So we are dealing with microvolts here. Anyway, this the shunt is put on the low side of the output, on the ground side. So you have on each side of the shunt between you have on the left side, to explain it better, a shunt B for here. The voltage gets negative the higher the current is flowing through the shunt. And we have connected the shunt, the low side of the shunt, that is more or less when it gets negative, to a resistor R18. And if we follow it, we go to another resistor R19, and the top of R19 is the wiper of a potentiometer that gives the top of this resistor 0 to 5 volts. And this thing is nothing more than a resistor divider with a variable top voltage and a variable bottom voltage, let's say so, yeah. And the midpoint of the resistor divider goes at pin 15. That's the negative input of one of the op amps. The positive input of the op amps goes again to a resistor divider that, if calculated, it will give 5 millivolts. Yeah, and this is the tipping point, more or less, when this thing goes below, when pin 15 goes below or above that, that triggers this op-amp to do something. Yeah, well, great explanation, huh? Not really. This is why I made a simplified design using a schematic simulator from Falstad. It's the first time I'm using that. It's this one. And I put the label of the resistors as it is on the schematic, so it can be followed. We have here the current potentiometer that is marked ATR on the PCB. We have R19, the resistor at the top of the divider, R18, the bottom of the divider, and connected to the low side of the shunt that is really 1.5 milliohm, very low. Why they do it? Probably to have everywhere this don't have to use different shunts. I don't know. The next thing is why this thing is so complicated, because we are dealing here with microvolts. Yeah, this is the problem. And if you bring microvolts from the one side of the PCB till the other side of the PCB where the TL494 resides, you will have a lot of noise. This is the only thought I can give you. This is just a thought. Yeah? This is my opinion. I don't know if it's correct, but I don't see any other reason why they do it like that complicated. Just to use these very low ohmic shunts and to reduce the probability of distortion of the signal till it goes to the inputs of the TL494. Anyway, so the midpoint of the resistor divider R19 and R18 goes to the negative, that's pin 15, and the positive pin 16 goes to the other divider that gives a tipping point of more or less 5 millivolts. This is not very accurate, the whole simulation, but it is ideal for you to see how it works and to play with it. Here we have the 5 volt that simulates the 5 volt reference, and for the ease of use I used just 12 volts as the output voltage and not 300 volts. It's unnecessary. This is just for understanding the whole circuit. Then we have a variable load resistor that is controlled with this slider here, and we have the potentiometer, this potentiometer that is controlled with this slider here. Now the potentiometer is set. These sliders are not very accurate. They jump quite a lot. You will see. It's set to more or less 250 milliamps. See what happens at the moment. We have pin 15. It is more positive than pin 16. Yeah, and the output is negative. This is why the LED is not lighting. If the LED here lights, that means that the PWM on the TL494 is getting narrower and is throttling back. The next thing is that from left to right, left is the highest load, right is the lowest load. So let's go a little bit higher, 283. Now we reached 283 and we are almost at 1. This is almost the same. And we already see that it's getting positive, the output. So the throttling already starts. And now we're a lot more negative than the pin 16. That means now we have the complete 5 volt output that throttles completely the PWM on the TL494. So let's go to a higher load, for example 1.7 amps. Of course this is going berserk. Here you set the threshold of the load itself. Yeah, let's go higher, not highest here. At the moment, with this shunt resistor, with this dimensioning of the resistors, we should not go more than 1.5 amps, but now we are at 1.7 amps. Of course, the output is throttled. Let's go back. we reach 1.5 amps. This is a lot more negative. Pin 15 is a lot more negative than pin 16, and we are in the green zone. I don't know how to do it to make it green or not. Anyway, that means now the PWM is not throttled. So this complete schematic here is the first time I'm using the FALSTAT simulation simulation software. It is very nice for easy things. It's the first time I draw it. It took me half an hour or something to find myself in what I have to do and how it works. The design here, what you see, will be available on request, on the comments. I can send you the design so you can play by yourself to understand it better. One important thing, if you go to the options and you go to other options, you have to put the decimal digits, the short format, to 3. It was at 1, and then you have this here. You do not see exactly what is happening. That's not enough, because really we're dealing with microvolts. Yeah. So let's put it back. Where is it? Where is it? Here it is. Other options. Let's give it to 3. OK. And watch the voltage on the shunt resistor. 1 milliohm, guys, for 1.6 amp. Ridiculous. Yeah? These are so small, the changes that happen here. Yeah, this is why probably they need this whole contraption. In my designs that I'm going to do, doing with the TL494, I'm not using this. This is far too complicated. And for what? I will use a shunt that is really usable for the current that I'm planning to draw maximum, and not just 1.5 milliamps. This is for I don't know, 30 amps or even more. Yeah, ridiculous. Look at here. We're using 5 millivolts, and it makes difference of a few millivolts to make this thing tip over. Yeah. Anyway, now you see it back. So this is more or less how it works. This is the whole magic here. In another complete reverse engineering of one of similar power supply like that, Chinese power supply, but different, a little bit different design. They do not use a potentiometer here. It is just fixed 12 volts, so 5 volts. That means it is they are just regulating the maximum current. That means if it's at 12 volt 33 amps, if it goes over 33 amps, then it throttles. That's all. The rest is more or less the same. But you will see this in another video, because it is quite different on the design of that. Yeah. So this is the design again. This is what I wanted to show you. Everyone that wants it, just write me in the comments and send me a mail. I will send it to him. So that's it for today. Guys, if you like my videos, this was a little shorter videos than normally, but it was just an explanation video. If you like my videos, if you like my content, please press the thumbs up. Consider subscribing my channel. This helps me a lot. It helps my channel to grow. Press the notification button so you get informed when I get back with new videos. And yeah, I checked again my statistics, and I see that most of my subscribers, more than 75%, most of my viewers, more than 75% are non-subscribers. Guys, if it is possible for you, just subscribe. It costs nothing, it is free, and it helps me a lot. Okay, one of my next videos will be the complete reverse engineering of this thing and all my, with the schematic, with everything, and with all my problems or surprises that I had with that and how it works. It's quite, it is a half bridge like the other one, but its function is quite different. You will see what I mean. So, till next time, thank you for watching. Cheers, guys, and be careful. Bye.